the equivalent capacitance. That is, I can replace any set of capacitors in parallel with a capacitor that's equivalent to those capacitors. It's going to equal to C1 plus C2 plus C3. For capacitors in series, the equivalent capacitance is going to be equal to 1 over C1 plus 1 over C2 plus however many capacitors you have. So this will be rule number 1. Rule number 2, capacitors in series, or in parallel rather, have the same voltage. We'll also have this rule for resistors in parallel. They'll all have the same voltage. Rule number 2 for capacitors in series is caps in series have the same charge. All right. Rule number 3. There really is no rule number 3 for capacitors. There would be a rule number 4, so I'm just going to leave 3 blank because there is a rule number 3 for capacitors in series. For capacitors in series, the sum of the individual voltages is equal to the total voltage. Or you could say V1 plus V2 plus V3 plus however many capacitors I have is equal to the total voltage. That might be the voltage of the battery. So for example, if I have 12 volts here and I have 8 volts here, then I must have 4 volts here because it has to add up to equal to 12. This is a rule called the loop rule. We'll see that when we get into resistor circuits next chapter. And then finally, the 4th rule, which is for both of them, is that Q is equal to CV. That's true for any capacitor. So it'll hold in general. It's sort of like, I know some of you are in the lab, it's sort of like the Ohm's law for capacitors, if you want to think of it in that way. So when we get to resistors circuits, we'll see a very similar set of rules that'll be a lot like this, but they'll be different in some cases. So for example, those of you that are in the lab will notice that the equivalent capacitance for capacitors is switched from what it is for resistors. Y'all recognize that? Y'all done resistors in series and parallel yet? Yeah. So the equivalent resistance for resistors in series actually looks like this form. If you forget, that is on your equation sheet. Let me show you. Hopefully you just have this equation sheet now and you're printed it out. Yeah, so here's our capacitors in parallel, and then this is our capacitors in series. Notice that it looks a little bit different, but those are the same. That I can rewrite this just by taking the inverse of it, as C equivalent is equal to 1 over C1 plus 1 over C2. But if you forget, those are there on the equation sheet. That's what they're there for. Okay? So those are our rules. I'm going to recap all those. I'll go over them in more detail and show you how they're applied. But just so you have them all written down in one place, you'll need to use them as you work through all the circuits. The simpler circuits where they're just series and parallel, and then also you'll need to use them for the combination circuits, where we have capacitors, let's say resistors, sorry, where you have capacitors that are in series and parallel, all mixed and matched together. All right, let's look first at capacitors in parallel. And again, sort of recapping those rules, so you'll see the same things over again. When I have capacitors in parallel, they're going to look like this. I'll have a certain voltage supply. This will be my battery. And then I can have 2 or more capacitors that are in parallel. Notice that I don't have any capacitors in series. So for example, I do not have 2 capacitors up here, because then that would be like a series circuit embedded within the parallel circuit. So when we have just these capacitors in parallel, like for example where I don't have a capacitor there, so that they're not have nothing in series, I'm going to have some rules that I'll follow. Remember, capacitors in parallel, a circuit with parallel capacitors, we'll have junctions. And that will help you to identify where those are. So here in this circuit, I come along, I usually go off the positive side of the battery. I look for a junction, and I see 1, 2, 3 separate parts to that junction. So that tells me that I have 3 branches in that capacitor circuit. You see the 3 separate parts to that junction? I have 1 here, 1 here, and then it breaks off again up here. I could draw this in a number of different ways. Like, for example, I could draw this circuit as well. That would look like this. It could, I could have it that would be the same circuit where I now have 3 junctions that break off 1, 2, 3 and go to those 3 separate things. I can move junctions around. As long as there are no electrical devices and there are no other junctions, I can compress all these down to a single point, and that's what I've done here. That might seem kind of silly here, but when we get to more complicated circuits, it won't be.
Why is that second horizontal not a junction?
The second horizontal?
Yes, so like on that second.
Okay, let me clarify because I'm going to erase this. Let me redraw it in a little more detail. I can take this second horizontal as a junction, all right? But I can think of it as this is my first junction right here, this is my second junction, and this junction goes up into this capacitor, and then my third junction is right here. That's why I can take this whole thing right here and just write it as a capacitor here, a capacitor here, and a capacitor here. That is the same part of this circuit. So if I redraw it, these are identical circuits. And then those 3 junctions become a little more apparent right here. So y'all see the three branches here? That similarly has 3 branches right here. What I've done is I've taken all of this and just compressed it down to a point. And often in circuit diagrams you'll see that because it saves space when they're drawing the circuit diagram. Okay? Being able to look at these is important. Just sort of being able to look at the diagram and sort through what the capacitors are doing. You'll get practice with that. Don't worry, you'll be pros at it by the end. Okay, so C1 and C2 or C3 or whatever, this is my rule, this is our rule number 2 actually. When they're in parallel, they have the same voltage across them. So if 2 capacitors are different, they also have different charges stored within them. All right, I don't like to use this word, but this should be obvious. It's meant to be an obvious statement that if they have the same voltage, say for example, I have a circuit that looks like this. I have 12 volts here. That means I also have 12 volts here and 12 volts here. So if I have different capacitors, say 1 microfarad, 2 microfarads, those are going to have different charges. This one will have, what will the charge be here? I know that Q is equal to CV. If I have 12 volts and 2 microfarads, what is my charge? It's going to be 24 microcoulombs, right? And then here I'll have 12 microcoulombs. Different capacitors will have different charges. I say that because when we get to capacitors in series, that's not going to be the case. But for capacitors in parallel, my different capacitors will have different charges. When electrical devices are connected in parallel, you can imagine that they are connected directly to the battery. So if I just, should I see, did I include that? No. So I can imagine that I have a battery. This is my 12 volt battery. I have my positive and negative leads, right? This is like a battery that looks like this in my symbol. And then I hook up a wire with a capacitor and I connect it to the battery. And then I hook up another wire with a capacitor and I connect it to the battery. So I like to think of capacitors in parallel like that instead of thinking of them like this, although these are identical. This is what it might look like if we hook it up, say, with a battery and a couple capacitors, and this is how we would represent it with a circuit diagram. But I like to think of it in this way because each capacitor then is hooked up to the same battery, and so they're each going to see 12 volts. I'm going to have 12 volts on this capacitor and 12 volts on this capacitor. And then that helps me to remember that capacitors in parallel have the same what? Do they have the same voltage or the same charge? They have the same voltage. Capacitors in parallel have the same voltage. We'll see that capacitors in series don't necessarily have the same voltage. All right. So here, let's just do this quick little example. Probably not going to have a simple parallel circuit like this on the test. They're really quick and easy. Probably going to give you one that's a little more complicated, but let's do it just to start. So here I just want to know what is the charge on C1 and C2. Well, you need to recognize that the voltage on each capacitor is going to be the same as the battery. So I'm going to have 10 volts here and 10 volts here. And then if I want to find Q1, Q1 is going to be C1 times V1. That's going to be 1 microfarad times 10 volts. And Q2, so that'll be 10 microcoulombs. Notice how I carried my micro through there, so I don't have to convert to SI units. I could just sort of carry it through. And then Q2, of course, is C2V2. That's 2 microfarads times 10 volts, which is equal to 20 microcoulombs. Okay? So 2 or more capacitors can be replaced by a single capacitor that has the same capacitance as the multiple capacitors in the circuits. You remember what we call that? If I replace a bunch of capacitors with a single capacitor, what do I call that single capacitor? It's an equivalent, right? It's an equivalent capacitor. You have a very similar thing with equivalent resistors, and it's a pretty common thing to simplify a circuit and replace it with an equivalent capacitor, and you'll certainly have to do that on the exam. So this is called the equivalent capacitance, because it's equal. And for capacitors in parallel, this equivalent capacitance is given as C1 plus C2 plus ... however many capacitors you have. So over here, my equivalent capacitance will equal to C1 plus C2, 1 plus 2 microfarads, which is equal to 3 microfarads. So here, my equivalent capacitance is 3 microfarads. Similarly, if I had more capacitors, if I had 1 microfarad, 1 microfarad, 2 microfarads, then this would be 2 plus 1 plus 1, which is equal to 4 microfarads. All right? Just add them up. Nothing complicated with resistors or capacitors in parallel. Just add up the values of the resistors. Let's try this one. Let me pull up your thing. You could see some multiple choice like this, but you're not going to see a free response, for sure. All right, what is the charge on the 3 millifarad capacitor? That's the topmost capacitor. Is it 6, 54, 8, 10, or 28.8 millicoulombs? All right, I'll stop at 40 seconds. Okay, good. B is right. All of these are going to have the same voltage. I have 18 volts here, 18 volts, 18 volts, 18 volts. Remember, it's as if each capacitor is hooked up individually to the battery or to the power supply. And if I want to know the charge on this capacitor, I say Q is equal to CV. That's 3 millifarads times 18 volts. That's equal to 54 millicoulombs. So 54 is the right answer. Let's see, some of you put A and C. Okay, well you got A probably because you had 18 divided by 3, right? Is that how you got A, most likely? And then C, not sure how you got C. You're just guessing. Okay? Alright? Could see some multiple choice on the exam like that. Now let's look at capacitors in series. These are a little more complicated, a little more difficult to deal with. If I have capacitors in series, they'd be hooked up like this. I can imagine them as my two metal plates here, my two metal plates here. My battery here is going to put a charge on this capacitor. All right? And in fact, I can think about, if I want to think about this circuit in a little bit different way, I can think about just taking this wire off and connecting it to ground. Remember how when I had the Van de Graaff generator in here, we connected the wire to ground, and I said all those excess charges, they went into the earth? That would be a similar thing if I connected it to ground. And so what would happen here is I would have charges that would go to this plate, and then it would induce charges onto this plate. So I get some positive charges on the first plate. That's going to induce charges on the next plate. And because I've induced charges on this plate in the middle, notice this whole thing in the middle is not touching at all. If I get 3 negative charges over here, I'm going to have 3 positive charges left over here. It's an induced charge, just like we dealt with in Chapter 1. So I'll get 3 positive charges here, and then this plate is going to suck up 3 negative charges onto it from the ground. So you can think of it as hooked up to a ground, or you can think of it as hooked up to the battery. It's largely the same. But I'm going to get equal and opposite charges on each of the plates. Now when I'm talking about the charge on a capacitor, I'm really talking about the charge on one of the plates. When we calculate that Q equals CV, because I'll get a positive charge on one plate and a negative charge on another plate. But they're both going to have the same magnitude. We don't usually distinguish between that. The equivalent capacitance is going to be, gave this to you before, but the equivalent capacitance is 1 over C1 plus 1 over C2 plus 1 over C3 plus however many capacitors I have. So go ahead and try this. What is the equivalent capacitance of this 3 and 6 microfarads? Try it out. You shouldn't need your calculator. In fact, try to do it without your calculator. You'll find that I'll give you really easy numbers, and if you just try to not use your calculator, I think you'll find it go a little faster. Doing the common denominator, adding up the numerators, looking the fraction. You can use your calculator for it. It's going to be 1 over 3 plus 1 over 6. And then what does that give us? It's going to be 2. Right. Listen, you'll find that I give you easy pairs of numbers. That's going to be 1 over 2 6 plus 1 6, which is 1 over 3 6, which is 1 over a half, which is equal to 2. So my equivalent capacitance here is going to be 2 microfarads. You'll find that I give you pretty easy sets of numbers. For example, I like to do 1 over 4 plus 1 over 4. I like to do 1 over 2 plus 1 over 2. I like to do 1 over, I think 3, 6, and 2. Is that right? That's 4 plus 2. Yeah. I like to do those combinations, a 3, 6, and a 2. microfarad, I like to do 1 over 3 plus 1 over 3 plus 1 over 3. So all these give you whole numbers, right? They do all give you, try them out, tell me what the whole numbers are. These are just combinations of capacitors that I like to use. You'll see these numbers for sure on the test. There's another one that I like to use. I forget what it is. What's this first one? 1 over a quarter plus a quarter. That's 2. 1 over a half is 2. 1 over a half plus a half is 1. That's 1 over 1. What about this 1/3 plus 1/6 plus 1/2? It's also equal to 1. That's like a 1 over 4/12 plus 2/12 plus 6/12, which is 1 over 12/12, which is just 1. And then this 1 over 1/3 plus 1/3 plus 1/3, that's 1. Right, so you'll see some very simple combinations of capacitors in series, so that you don't have to pull out the calculator every time. In fact, if you just sort of, I would say memorize them, but be familiar with these combinations of capacitors, it'll make the test go a lot faster, because you'll see a 3 and a 6, and say, oh, I don't even have to think about that, that's 2 microfarads. Or you'll see a 4 and a 4, and you say, oh, that's 2 microfarads, or a 2 and a 2, and that's 1, and on and on. So it will behoove you to be familiar with those combinations of series capacitors. If not, that's fine too. You can just work it out on the test. Okay. So remember our rules. Capacitors in series have the same charge. Also, add a little addendum to this. They have the same charge as the equivalent capacitance. So whatever charge I have on the equivalent capacitance is also going to be on each individual capacitor. Let me show you what I mean. So let's consider this circuit. I have 2 capacitors, and I want to know what is the potential difference across C1 and C2. C1 is 2 microfarads, C2 is 4 microfarads. Now, let me first off just show you a little trick. Oh no, this one isn't a very good one. I'll show you another trick with another one later. Oh, now let's make this, instead of 8 volts, and I'll show you a trick. Let's make this 12 volts. Let me write another little rule. This isn't for either capacitors in series or parallel, it's for both. But a big capacitor has a small voltage. A small capacitor has a big voltage. That comes about from this Q equals CV. So if C is big, V is small, given a constant charge. So I can tell you then that this is the smaller capacitor, so it's going to have a bigger or a smaller voltage than this capacitor. Will this one have a bigger or smaller voltage? It will have a bigger voltage. And by how much bigger is it going to be? The 2 microfarad voltage. By what amount is the voltage on this capacitor going to be bigger than this capacitor? It's going to be twice as big, because this is half as small. It's half the capacitance of this capacitor. So it'll have a capacitance that is half that, or excuse me, twice that of C2. Remember, there's another rule that says that the voltages all have to add up to equal the total voltage. So this voltage has to be equal to this voltage plus this voltage. Can you think of 2 numbers that would add up equal to 12? That would be one twice the size of the other? 8 and 4, 4 and 8. So I know that these 2 capacitors are going to have a 4 and an 8 voltage. Which one will this have, the 8 or the 4? The 8, and then this one will have the 4 volts. All right, so often when you look at these circuits, I'll give you numbers such that you can do that without ever putting your pencil to the paper. You can just say, oh, this has to be 8 and 4 volts because of the way that the voltages have to be distributed. Hopefully you'll get to that point where you can just look at circuits like this and tell yourself right off what is the voltage. But if not, there's a process to get to that. So let's go through that process. And then as we go along doing samples, I'll show you both ways. That is, you can just look at the circuit and see how the voltages are distributed, or you can go through this sort of more lengthy process. The first thing you want to do is find the equivalent capacitance. The equivalent capacitance of this one is going to be 1/2 plus 1/4. This one is not a simple one. It's going to be 2/4 plus 1/4, which is 3/4 or 4/3. So the equivalent is going to be 4/3 microfarads. I can redraw that circuit. It'll look like this. And remember, we're doing 12 volts here. Since the capacitors are in series, they have the same charge. Not only the same charge, but also the same charge as the equivalent. All right, so my Q equivalent, that is the charge on my equivalent capacitor, is going to equal to C equivalent times the voltage. My C equivalent was, what was that, 4/3 microfarads times the voltage, which is 12 volts. That's going to be 3 goes into 12, 4. That's going to be 16 microcoulombs. 4/3 of 12 is 16. So what that tells us, if I think about my circuit again, remember capacitors in series have the same charge, so I'm going to have 16 microcoulombs here and 16 microcoulombs here. Try to keep these straight with capacitors in parallel, because capacitors in parallel don't have the same charge, they have the same voltage. Okay? But these capacitors are in series and they have the same charge, so if I want to find the voltage, I say, I know that Q is equal to CV, so I say V1 is Q1 divided by C1, and V2 is Q2 divided by C2. That's going to be 16 microcoulombs divided by C1. What was C1? 2 microfarads. That's equal to 8 volts. And then this is going to be 16 microcoulombs divided by 4 microfarads. Notice the micros cancel out, and that leaves me with 4 volts. So remember, this is what we said before, that this one has to have 8 volts, and this one has to have 4 volts. Because this first capacitor was the smaller of the two, it has a bigger voltage. The second capacitor is the bigger of the two, it has a smaller voltage. Also note that C1, okay, so I just said this, but let me just put this in words. C1, which has half the capacitance, of C2, has twice the voltage. Remember, Q is CV. If C is big, V is small. Or if C is small, V is big. Getting that straight in your head will really help you a lot on this next test, because it'll help you to see the circuits a lot better. Okay? I find that with capacitor circuits, there's not really a whole lot to them. There aren't really a whole lot of formulae or whatever. It's really just the equivalent capacitance, Q equals CV, and that's about it. And then you have these few simple rules. And on their own, they're simple, but it's when you put them all together, they sort of all start jumbling together. So that's what makes it difficult with capacitor circuits. All right? Okay, also when electrical devices are in series, the sum of their potentials, or the sum of their voltages, is equal to the voltage of the source voltage, I'll call it. In this case, the source voltage is the battery. But we will see that in more complicated circuits, that the source voltage won't be the battery. So V, this is one of our rules, that V is equal to V1 plus V2 plus ... Remember, this is called the loop rule. We'll see it again in chapter 4. And so in this case, we had 12 volts is equal to 8 volts plus 4 volts. You'll find that there are lots of little checks that you can make when you're working with circuits, that you can get your answer in one place, and then you can check it to make sure that you did it correctly by something like this. So if you go through this process and say up here, when you calculate the voltages, let's say you don't calculate 8 and 4 volts, you calculate 6 and 2 volts. Then you know that you did something wrong, because 6 plus 2 doesn't add up to equal to 12. So usually if you get an answer that checks out in that way, then you've done it correctly and you have the right answer. Okay, let's do a clicker question here. What is the potential across the 24 microfarad capacitor? First of all, before you go through that process, why don't you just look at it, think about what are some of the options that are not really feasible, and then maybe you can pick out the best answer without ever actually putting your pencil to the paper. As you see that 24 microfarad capacitor, think to yourself, gosh, does it have to have a bigger voltage or a smaller voltage? Because it's a big old capacitor in comparison to 3, 6, and 12. And then by what amount must it be bigger or smaller? If you finish this one, I'm going to put another one down here below. Go ahead and work on this one, but I'm going to put another question that's similar. All right, I'll stop this one at 2 minutes. So just guess. We're doing the one up top here at 2 minutes. Okay, great. That is right. Listen, I can get rid of 2 answers right off because they're just way too big. I know that the voltage across this, there's no way it can be 29 volts because that would exceed the voltage of the battery, and that would violate the loop rule. Likewise, in a similar way, I can say that this one can't be a right answer because if this one's 18 volts, that means all these other 3 have to have 0 volts. And I know that's not the case. That can't be true. And then I can sort of reason out these other 2. These are both less than 18. You know, I've already whittled it down to one answer, but I can look at these and I can ask myself, well, this one has to have the smaller of the 2 volts, the smaller of the 4 voltages here. So let's just try this 1.2. I think that this might be the answer, and so let's try it, because this is the smaller of these 2 numbers. And so if that voltage is 1.2 volts, that means that the voltage here has to be what? It has to be 2.4 volts, right? Because that capacitor is half the size, and so it has to have twice the voltage. And this voltage has to be what? 4.8. And this voltage has to be 9.6. And if you add all those up, you get 18 volts. And bam, that's your answer. It has to be 8. It has to be the 1.2. Okay? Let me show you another way. Sort of the hard way to do this is to first find the equivalent capacitance. And it's a little tedious to do this because the numbers don't work out even. The equivalent capacitance is 1 over a third plus a sixth plus a 12th plus a 24th. And then that works out to be 24/15, yeah, 1.6. I'm going to keep it in fraction. microfarads, or 1.6 if you wanted to do that. All right, now the equivalent capacitance then is that. Then I would find the equivalent charge, which is going to be C equivalent times the voltage. That's 24 over 15 times 18. $144 over 5. What is that in decimal form? 28.8. So each of these have 28.8 microcoulombs. So now I come to this one, and I say, well, I know the charge, I know the capacitance, I want to know the voltage. That's V is Q over C, which is going to be 28.8 over 24, which is going to be 1.2 volts. And that's our answer. Okay, so that's sort of the hard way. That way will always work. But you will notice when I give you circuits that there will usually be an easier way to do it that often will not require much work at all. Okay? You have to be pretty quick on your feet though to do that, and it takes a lot of practice to sort of get to that point where you can look at a circuit and say, well, this is what it is. So I recommend that you know this process. Find the equivalent capacitance, find the charge on that equivalent capacitance. Recognize that that charge is the same on all the capacitors in series, and then find the voltage. Because that will never fail you. But again, it will often be an easier way. Let's try this question. Right here. I have three 2 microfarad capacitors in series with a 12-volt battery. What is the voltage on the one that I've circled? The one to the far right. Okay, awesome. Just a few more seconds. I'll stop at 30. And then I'm going to give you one more, actually. Go ahead and finish that, and I'll give you another one. This will be our last one. What is the voltage here? This is not the one that's running, but what is the voltage on this one? I'm going to stop this one now. Awesome, B is right. These are identical capacitors, so they're all going to have the same voltage. 4 volts, 4 volts, 4 volts. They're also all going to have the same charge. They will all have, well, let's see, C times V, they'll all have 8 microcoulombs of charge. Remember, they will always have the same charge. They may not necessarily always have the same voltage, but in this case, because they were identical capacitors, they had the same voltage. Do you have a question, Steve?
No.
No. Okay. Did I tell you about how the police came to my house the other night? Yeah, they came in, the lights are on. They came, knocked on my door, boom, 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 boom. The dog went crazy, middle of the night. And I went to the door, opened the door, I'm like, yes, sir, we're going to do for you. And he's like, sir, can I just have a quick word with you? I said, yeah, sure. How about velocity? Try that next time the cops are asking you a question. Can I have a quick word? That was a joke. Like, the cops didn't really come to my house. I didn't really say that. All right. Can we do this one? No, we didn't do this one. So try this one out over here. What's the voltage across the 6 microfarad? All right, I'll stop at 20. Okay, awesome. B is right. We had this one before, actually. right? So I know that these voltages have to add up equal to 12. I know that this is the smaller capacitor, so it's going to have the bigger voltage by a factor of 2, because it's half the size of the 6 microfarad. So that tells me then that I'm going to have 8 volts here and 4 volts here. So B is the right answer. Or you could find the equivalent capacitance. The equivalent capacitance is equal to 2. 1 over a third plus a sixth is 2. The equivalent charge then is going to be CV is 24 microfarads. So I'll have 24 microfarads here. 24 divided by 6 is 4. 24 divided by 3 is 8. That's sort of the longer steps that you'd take, just like we did before. Okay? Capacitors in series are a lot more difficult than capacitors in parallel. But even more difficult is when we combine them all up, and that's what we're going to do next. And that's more what you'll see on your test. Okay, so usually when we have circuits, you're going to have capacitors and resistors and inductors all mixed in together. And we'll get into some of those, or at least some simple circuits of some of those towards the end of the semester. But right now we're just dealing with capacitors. And so usually you're going to have them in a combination of series and parallel combinations. We apply the same rules, but we just have to treat those series and parallel branches separately. So it's like we separate them out. So here, first of all, I want to find what is the equivalent capacitance for this circuit. And then I also want to find the potential difference across the 3 microfarad capacitor. Actually, on your exam, I'm going to ask you for the equivalent capacitance and the voltage and the charge on every capacitor. But it's not that hard. You'll see that if you can find one of them, you can find all of them. So first, if we want to find the equivalent capacitance, we start with the smallest part that's either series or parallel. What is the smallest part that's series or either series or parallel in this circuit? That one little chunk at the top. Right, I have two microfarad capacitors up top here. These are only series. So I'm going to take this and find the equivalent. Gosh, what is the equivalent of a 2 and 2 in series? It's 1, right. So my 2 and 2 in series is going to be 1. I'm going to treat it first. I like to redraw my circuit each time, and I recommend that you do that as well, just to start. It'll help you sort of see the circuit. So this is now going to be a 1 microfarad with a 3 microfarad. Oh, this one doesn't have easy numbers, sorry. And a 7 microfarad. And then I combine that with a 1 microfarad. I go down there. Now what am I going to combine? This whole thing. All right, so I combine that. What is the equivalent of that parallel circuit? It's 11, right. So I have now my 10-volt battery with an 11 microfarad and a 1 microfarad. Looks like that. And then I combine these two. Are these in series or parallel? These are in series. Even though they sort of look like they're in parallel, because they're like this, there's no junction in between them. There's a bend in the wire. But notice that I could just as easily draw this circuit so that it looks like this, if that helps you. Fine. So those are the same circuits. And then I find the equivalent of that. This does not work out right. That works out to be 0.92. I think. Let's see. Yeah, 0.92. 11/12 or 0.92 microfarads. So that's my equivalent capacitance. This one is a little bit simpler than you'll see on the test. We'll work through some that are like on the test in just a bit. Okay, that's my equivalent capacitance. Now I also want to know what is the potential difference across the 3 microfarad capacitor. Across this capacitor right here, which is the same as this capacitor up here. Okay, and this is where I start working backwards. I know that these two capacitors will have the same charge. And I know if I find the voltage on this, so I can find that charge, because that charge will also be the capacitor that's on this capacitor, the charge that's on this capacitor. If I find the charge on this capacitor, I can find the voltage, because I know C, I know Q. If I find the voltage on this, how will that compare to these voltages? Well, these voltages will be less, the same, or more than the voltage on this capacitor.
The same.
It's going to be the same. Capacitors in parallel have the same what?
Voltage.
Voltage. They also have the same voltage as their equivalent capacitor. Capacitors in parallel have the same voltage. They also have the same voltage as their equivalent capacitor. So, if I find the voltage on the 11 microfarad capacitor, I'm done. All right, so let's do that. My equivalent charge is C equivalent times V. That's going to be 0.92 times 10 volts, or 9.2 microcoulombs. So I have 9.2 microcoulombs here, 9.2 microcoulombs here. Then I can find the voltage here. V is equal to Q divided by C. 9.2 divided by 11, which is 0.84 volts. So I have 0.84 volts here. By the way, what's my voltage going to be here? On the 1 microfarad. 9.16. 10 minus 0.84. Right, but I don't need that. That 0.84 then is right here. Look, I can go ahead and do all my voltages, because I'm also going to have 0.84 here, 0.84 here, and as we said, 9.16 volts here. And then you're done. If you know two quantities on any capacitor, you can find the other quantities just from Q equals C. Okay? Y'all don't look nearly as excited about that as you should be. Are you excited about it? Okay. I think they're kind of fun. They're kind of like, I don't know, Sudoku or whatever. Let's try this quick test, and we'll wrap it up. What is the equivalent capacitance of this circuit? Try just looking at it for a second without actually putting your pencil to the paper. All right, let's stop in about 10 seconds, 15 seconds maybe. I'll stop at 145, 145. 145. Just guess if you're not sure. Okay, so we're all over the board on this. Where am I going to start first? The 2. The 2 and the 2. You think, oh gosh, 2 and 2 in series, that's a 1. So I can replace this then with a 1. What's that, a 3? A 1 and a 3 with a 4. And now I do the 1 and the 3. When they're in parallel, what do? I just add them up. So it's going to be 4 and 4. And then you think, gosh, a 4 and a 4 in series, I've seen that before. That's a what? That's a 2. So the answer is A, 2. My 4 and 4 in series is 1 over 1 over 4 plus 1 over 4. That's equal to 2. And by the way, this 1 over 2 plus 1 over 2, if you weren't sure about that, that's equal to 1. That's where I got the 1 that was right here. Okay? Alrighty? That's all, but I just want a quick little word, not velocity, but a quick little word. This usually doesn't come up in the class so much, but in the lab it's kind of a big deal. Women, for some reason, I don't know, y'all been told that you can't do circuits or whatever, or something, I don't know. Y'all knew these just as well as the guys, or even better. So just don't let that sort of impede your thought about what you can do, because y'all are great students. In the lab all the time, I can't do circuits, but it's true, you can do circuits just as well as anybody else. Okay? Have a great day.